In our previous lecture, we'd managed to take a simplicial complex and drag it kicking and screaming into the world of algebra of vector spaces and linear maps. Let's remind ourselves what we got at the end of this process. We had a chain complex. So we wrote them as CD. And this is over some field F. This looks like C0. That's a vector space. C1, C2, these are all vector spaces. They go all the way up. D0, D1 are linear maps. And so that's part of the definition. And then the most important bit of it is dk composed with dk plus 1, which is the map going from ck plus 1 to ck minus 1, is always 0. Which is not saying that either ck plus 1 or ck minus 1 has to be 0. It could be some complicated vector space, but when you compose these two linear maps, you always get the send everything to 0 map from the first to the second. Okay, so as remarked last time, this is the same as saying that the kernel of dk contains the image of dk plus 1 inside the chain group ck. That's what that's saying. Okay, so here is the most important definition, not just of the week, but maybe of the whole course. The kth homology group of this chain complex CD is the quotient, and here's how we write it. HK of CD is the quotient of kernel dk by the image of dk plus 1. So these are two subspaces of CK, the K chain group, and the image of dk plus 1 by the definition of a chain complex is forced to be a subspace of the kernel of dk, and homology is measuring how close this image comes to being the entire kernel. So it's measuring the difference between the incoming map at CK's image and the outgoing map from CK's kernel. Just as a sort of side note, kernel dk is called the subspace. It's this vector space of k cycles, and image of dk plus 1 is called the subspace of k boundaries. So informally, homology in this terminology is cycles up to boundaries. Okay, so as defined here, a homology group is just a vector space. It's the quotient of two vector spaces, so it's a vector space over F, and maybe the most important thing for a vector space is its dimension. So the dimension of of the homology of CD is called the kth Betti number. Of this chain complex CD. Now note, in general, we haven't placed any bounds on the dimensions of the chain groups. So the way I've written it right now, in general, this quotient could be infinite dimensional, that quotient that defines homology. So this could be infinity, for instance. But we are not going to be so interested in arbitrary sequences of vector spaces and maps that square to 0. Our interest is in the ones that come from simplicial complexes. So note, when the chain complex that we started with is the simplicial chain complex, how had we written it? C bullet K partial K of a simplicial complex. Then the Betti numbers are always finite, because in this case, the dimension of CK is always going to be the number of K simplices, which is less than plus infinity. So nothing can actually blow up to infinity when you have a simplicial chain complex. The other thing to note is that when you have a simplicial chain complex, this whole notation becomes really, really cumbersome. H of C of K, D of K, or something like that. So for simplicial chain complexes, we write the homology groups simply as, let's say, HK of K, or if you want to really emphasize the choice of the field, you can write K and then separated by field, just to say that everything I say is going to be a vector space over F. We use the field F to generate all our coefficients. Okay, so maybe we should see a few examples of computing homology. So the simplest example is the homology of the solid zero simplex with coefficients in any field. So note that the chain complex is just, well, what do you have? You have a single zero-dimensional simplex, so that's the chain group in zero, and you have no other simplices at all. There's nothing there. So the only non-trivial kernel is the one for this map D0, which has dimension 1, and the image of the incoming map D1 is, of course, there's nothing there, it's 0. So HK of delta 0 with F coefficients is going to be, let's just, instead of writing the group, let's just write its dimension, because that's as good. We have a vector space, so knowing its dimension is just as good as knowing the space up to isomorphism. So this is going to be 1 if K equals 0, and 0 for all other K. If you want a bit of a challenge, you should try the boundary of the hollow 2 simplex with coefficients in F. Now the chain complex is much, much fancier. So if you remember, it looks something like the simplicial complex is going to be the hollow 2 simplex. So we make its boundary and then don't fill it in. And now there's going to be a map that is non-trivial between two chain groups that are non-trivial. So it won't be as easy as the previous computation, which is to say, so you have 3 vertices, you have 3 edges, and then you have no 2 simplices, no 3 simplices, all of that is 0, that's 0. So there's some matrix here, which I guess we should call D1 or del1K or something like that if we're being fancy. And let's see what this matrix D1 looks like. It's going to have all the edges indexing the columns 0, 1, 0, 2, 1, 2, and it's going to have the 3 vertices. This is just the adjacency matrix for the graph that this hollow 2 simplex creates. So this is going to be -1, 1, and -1, 1 there, 0, -1, 1. Well, if you take the second column and subtract the first column, you should get the third column, which means that this thing has rank 2. because the 3 columns are not linearly independent. Now, if this matrix has rank 2, then its image is 2-dimensional and its kernel is 1-dimensional. And therefore, HK of this hollow 2-simplex with coefficients in F has the dimension, which is the Betti number, is just going to be 1 if K equals 0 or 1 and 0 otherwise. Now, the 1 you got for K equals 0 is because 1 equals 3 minus 2, and the 1 you get for K equals 1 is because 1 equals 1 minus 0. So your job is to sort of figure out why those are the two numbers being subtracted in each case to get 1. Okay, good. So let's see. It seems that if all you care about are the Betti numbers and not, anything more intricate about the homology groups themselves, then the ranks of these boundary maps, these ranks of D1, D2, and so on, are playing an important role. And you can make this very, very precise. So let C, D be a chain complex. And again, I'm not going to insist that this comes from a simplicial complex. This is any sequence of vector spaces and linear maps so that adjacent 1 squared is 0. So we're going to force, however, all the chain groups to be finite dimensional. So dimension of CK, I'm going to call this NK, which is always going to be less than infinity. And rank of DK, which I'm going to call RK. And this, because it's going from CK to CK minus 1, and both of those have finite dimension, this rank is also automatically finite. Then the Betti number of CD, which is basically the dimension of homology, of the kth homology of CD, is always equal to NK minus the sum of the ranks. So this proof is not very difficult. And so, because it's not very difficult, I am willing to do it here on camera, and I hope nothing goes wrong as we go through the proof. Okay, so HK is the kernel. I'm not going to write CD every time. So this is the kernel of DK quotient, the image of DK plus 1. So the dimension is going to be the dimension of DK minus the dimension, sorry, not the dimension of DK. This is going to be the dimension of the kernel of DK minus the dimension of the image of DK plus 1. There, that's the way it makes sense. Now, by the rank nullity theorem, which maybe I should say, rank nullity, DK is going from CK to CK minus 1, and if its rank is RK, then the dimension of the kernel is going to be NK minus RK. And the dimension of the image of DK plus 1, of course, is just its rank. That's the definition of rank. So this is NK minus, and then you can combine the two rank terms here if you like. So this is now a complete recipe for computing the dimensions of homology groups, and therefore knowing the homology groups of any simplicial chain complex, at least, up to isomorphism, because all you cared about was its dimension. What you need is the ability to compute the rank of every boundary matrix, D2, D1, D0, all the way up, because you need all of them. You need these RKs to get out the Betti numbers. So, good. That's pretty much all there is if all you care about computing are the Betti numbers. But we can compute more. And by more, I mean basis elements for HK for all dimensions k bigger than 0. Which is to say, it's not just, okay, yes, we know what the dimension of this group is, as it's a vector space, so we know what the dimension of the vector space is. We can also compute in terms of linear combinations of simplices over the field F, what chains generate the homology group. So to do this, we're going to need a bit of algebra, which goes beyond the rank nullity theorem. And before I do any algebra, I want to show you the basic picture. And the basic picture is best illustrated not in the context of arbitrary chain complexes, but rather in the context of simplicial chain complexes, the ones that come from actual. So here's the basic idea. So I'm going to try and draw a chain complex in sort of a ridiculous way. So here is dimension C, the 0 chains, the 1 chains, the 2 chains, the 3 chains, and so on. And of course, these are all vector spaces. So just think of them as being generated by some basis elements. And what are the basis elements when you have a simplicial complex? Well, the basis elements in dimension 0 are just all the vertices of your simplicial complex. So dots, right? That's what they are. The basis elements for the 1 chains are all the edges, so those look like lines. The basis elements for all the 2 simplices, for the second chain group are all the 2 simplices, so solid triangles. Here you get solid tetrahedra, and hopefully you get the idea. You could keep going with C4 and C5 and so on. And what the boundary maps here are doing, so here is D1, D2, D3, is that up to plus or minus 1 coefficients in the field, they're linking each edge to its 2 faces, which are just going to be vertices. It's linking each 2 simplex to its 3 faces, which are going to be the 3 edges. It's linking each tetrahedron to its 4 faces, and so on. So if you think about this picture, the descriptions of the vector spaces are beautiful and geometric. Each basis element is a piece of K. It's a solid, visceral, you can feel it. It's like a piece of the simplicial complex. I mean, it lives inside the geometric realization. You can realize it as a subspace of the geometric realization and so on. If you change the basis and diagonalize these matrices, all of them, then you would take the same chain complex and you'd have a very different picture, even though it was the same chain complex. So you still have the same chain groups, still C0, still C1, still C2, still C3, and now you have something else on top of everything. You're going to have, instead of these nice geometric simplices, you're going to end up with linear combinations of simplices, right? So there's each dot here is not a vertex. It's a linear combination over F coefficients of vertices. Each dot here is not an edge. It's a linear combination of edges. Similarly, you get linear combinations of 2 simplices, linear combinations of 3 simplices, and so on all the way up. And because your matrix is diagonal, meaning it only has entries along, it could be a rectangular matrix, and it will be if, for instance, C3 and C2 have different dimensions. You won't get a square matrix. But if all the non-zero entries are concentrated on the diagonal, then there is at most 1 pairing that you can make. I mean, you're not allowed to fan out because that would require a column with lots of non-zero entries, and we can have at most 1. Similarly, you can't have a lot of things coming in. There's going to be at most 1 thing coming in because each row also has at most 1 non-zero entry. And you won't have anything going 2 steps across. There's not going to be a basis element that gets mapped to something non-zero 2 steps down, because remember, when you compose dk plus 1 with dk, you get 0. So everything just has this beautiful structure where, the maps have this beautiful structure where things just get paired up adjacently, and there's no sort of length 3 pairing. There's always across ck plus 1, or ck minus 1. So things in C2 can only pair with C1 or C3. And this is an exclusive pairing because you have diagonal matrices whose square gives you 0. The point of all this is, if you look at the source of one of these pairings, right? So they're always going from left to right. And similarly, this one is in the image of D2 because it gets hit by something in D2. So anything that is the source or target of an arrow is either not a cycle or it is a boundary, right? Not being in the kernel means not a cycle, and being in the image means being a boundary. So all the unpaired basis elements, which I'm circling here in red, these are going to be the generators of homology. And we will see how to compute them precisely in the next lecture.